Up where we left off on Wednesday. Last thing that we were talking about on Wednesday was our thyroid gland. We learned that there were two major hormones, T3 and T4, that the thyroid releases to increase our metabolic rate, okay, and along with some other things. Okay. There is a third hormone that the thyroid produces called calcitonin, which by its name should be an easy indicator of its role with regulating calcium in our body. We produce this hormone in response to hypercalcemia. Hyper is the prefix once again that means high. So hypercalcemia is a word that means high blood calcium. Okay. Within our bones, where we store most of our calcium, we have cells called osteoclasts. Osteoclasts are cells that will break down bone, performing what we call bone resorption, and release the bone as calcium into our blood. Well, if our blood calcium is elevated, we don't want those cells being active. So calcitonin lowers the activity or decreases the activity of osteoclasts. At the same time, we also accelerate the uptake of calcium and phosphates into bone matrix, which is actually done by way of cells called osteoblasts. And so we elevate blasts, we inhibit the clasts. Now, we might end up taking too much calcium from our blood, and that would cause a condition called hypocalcemia, which is going to trigger the release of this hormone. Actually, these hormones, because there's two of them listed on this page. The easiest named hormone, in my opinion, is parathyroid hormone, released by the parathyroid glands. Couldn't be any easier for knowing who secretes parathyroid hormone because it tells you exactly who it is. Your parathyroid glands are typically four small glands located on actually the back of the thyroid, and they are made up of cells that produce the parathyroid hormone, or parathormone as it's sometimes known as, in response to hypocalcemia, which is the fancy way to describe low blood calcium. Now, instead of decreasing the activity of osteoclasts, this hormone increases their activity, which elevates bone resorption or bone breakdown, thereby releasing the calcium into the blood. PTH will also act on the kidneys, so it's targeting the kidneys to slow the rate at which we lose calcium and magnesium in our blood, or from our blood into urine. So we end up peeing out less calcium. Also increases the release of phosphate ions into urine to help regulate certain things, because phosphate ions are also released into our blood during bone resorption. Okay. So we do want to get out the phosphates. We don't want to get rid of the calcium and magnesium. PTH stimulates the release of a third hormone related to calcium, and that's called calcitriol. But it's important that you know this, so everybody pay attention. Calcitriol is a hormone that's not released by the parathyroids, which can be confusing because we're talking about it on this slide. Calcitriol is a hormone that's released by the kidneys. Okay, so make sure you know the kidneys are who secretes calcitriol. Calcitriol is actually the active form of vitamin D. You might know vitamin D comes from the sun. So we convert it to calcitriol in our kidneys, and in the case of its release, we will increase calcium and magnesium absorption by the GI tract into our blood. So we end up pulling in more calcium from the things that we ingest, okay, therefore increasing blood calcium levels. Now, unlike T3 and T4, which were stimulated by hormones coming down from the anterior pituitary and hypothalamus, the release of calcitonin calcitriol and parathyroid hormone is strictly related to calcium levels. So it's a chemical concentration stimulus. On this figure here, we show the relationship that exists between those three hormones. At point 1 here, our blood calcium levels are high. Hypercalcemia stimulates the release of calcitonin. Calcitonin will lower calcium levels through the various things that it does. If our blood calcium level drops too much, we'll release parathyroid hormone from the 4 parathyroid glands. Parathyroid hormone, along with calcitriol that it stimulates to release from the kidneys, will help to elevate it. Okay, and it's just a nice weave of processes. Once again, we talked the other day about hormone relationships. We can describe calcitonin and parathyroid hormone as antagonistic in their relationship because they are opposite in what they do. Alright, our next set of claims are similar to the pituitary. We talked about the anterior and posterior pituitary on Wednesday, and we learned that even though the two structures are located right next to each other, they were completely and utterly different from one another. The same thing occurs with the adrenal glands. The two parts are called the adrenal cortex, which is on the outside. The adrenal cortex is something that we haven't talked about before. It collectively produces the corticosteroid hormones from 3 different parts of it, whereas the adrenal medulla we've discussed before. Remember, that's the part of the gland that has the chromaffin cells that are activated to release epi and norepi in fight or flight situations, which we know fight or flight situations involve which division of the autonomic nervous system? The sympathetic nervous system. And so the adrenal medulla effectively becomes just an extension of the sympathetic nervous system. Okay. And it releases those hormones, especially epi. 80% of the hormones released there are epi, but also norepi and a little bit of dopamine into the blood, doing things that help us resist a fight or flight situation, making us better ability or have a better ability to perform physical activity, increasing heart rate and blood pressure and cardiac output, ATP production, and yada yada yada. All those wonderful things that I just tested you on the other day. Let's talk now about the brand new part of the adrenal glands, the adrenal cortex. The adrenal cortex is made up of 3 different distinct zones or regions, and each of those secretes a different set of hormones. Now you might see in this page a lot of the prefix cort, or cortical, or cortex. Those all kind of go together. These hormones are collectively called corticosteroids. Cortico for cortex, and steroids because they are steroid in classification or chemical makeup. Let's talk first about the mineralocorticoids, which come from the zona glomerulosa, and they affect the homeostasis of our minerals. Specifically, we're talking about our ions. The major or principal mineralocorticoid is aldosterone, which has a fun nickname, the salt-retaining hormone, because that's what it does. It retains our salt. What's salt? Well, we know it's sodium chloride. If it's table salt, it could also be potassium chloride. And if we retain salt, that means we're going to help elevate those levels. Specifically, the 2 major ions that aldosterone regulates are sodium and potassium. Now, when you retain salt, you're going to also retain water. And that's going to affect our blood volume, which is the amount of blood we have, and therefore blood pressure. What do you think happens when we retain water? Does volume go up or down in our blood? Up, because our blood is made up of a lot of water. So if there's more water, there's more blood. So therefore, what's going to happen to blood pressure, Blair? Is it going to go up or down? If volume goes up, pressure goes up. Good. Okay. So aldosterone helps elevate blood vessel or blood volume and blood pressure. So we'll talk about it later in the semester when we talk about blood volume and blood pressure when we get to the cardiovascular system. We'll talk about it when we get to the urinary system with its relationship in retaining water. Okay. We're going to talk about this very complicated network or mechanism called the renin-angiotensin-aldosterone mechanism later in the semester. We could talk about it right now. I feel like you've got enough on your plate as it is, that I'm going to save this for later in the semester. If you look here on the next slide, this figure demonstrates how complicated it is. It involves our kidneys, where renin is produced. It involves the lungs, which do some converting of angiotensin. And then it involves the adrenal cortex, where aldosterone is released. It's a series of events that ultimately does a lot related to your cardiovascular system. Blood pressure, blood volume, constriction of vessels, etc. So we'll get to it and talk about it when we talk about blood pressure regulation. For now, what's presented there is all you really need to worry about. The glucocorticoids are going to come from the middle fasciculata. And based on its name as a glucocorticoid, you can guess it's going to be involved with glucose homeostasis. The principal hormone here is called cortisol, which also has a fancy nickname, the stress hormone, which is what we produce to fight off stressful situations. Now, in order to fight off stress, we need one big old thing, energy. Energy in the form of ATP. How do we get energy? Typically, it's from the breakdown of carbs and fats. And cortisol helps us make carbs, and it helps us break down fats. Over here on the board, I left this up from last class. I've got 6 terms. 2 of these are discussed right here. I will go ahead and write these out if you haven't already. Some of you are doing it right now. Our first term is something that we'll talk about later in the semester, which is where we actually take glucose and make ATP directly from it. That's called glycolysis. The second term is called glycogenolysis, which is spelled and sounds very similar to glycolysis. Glycogenolysis, with the word glycogen in it, is the breakdown of glycogen. Glycogen is the stored form of glucose, so we break down glycogen into glucose so that we can then make ATP from it. Both of those words end in lysis. Lysis is a term that means breakdown. We've also got some words there that say genesis, which not break down, but genesis means to build up. The term that's listed here on or under cortisol is gluconeogenesis, which is where we can make glucose from things like amino acids, fatty acids, lactic acid, which are all non-carbohydrate sources. That way we can use that glucose to make ATP, which helps us resist stress. The other genesis is glycogenesis, which we'll talk about here in a minute with a hormone from the pancreas. Glycogenesis has the word glycogen and genesis in it, is the opposite of glycogenolysis, and that is the making of glycogen from glucose. What's also listed on this page is lipolysis, which begins with the prefix lip, which we know lipids are fats. So, and it ends in lysis, we know litholysis or lipolysis is the breakdown of fats, like the triglycerides that we've learned about before, and 2,3 fatty acids and glycerol molecules, versus lipogenesis, which is where we make lipids and we build them up. We're going to talk about these 6 things throughout the next couple of slides. Okay. 2 of them are discussed right here. Lipolysis, breakdown of fats; gluconeogenesis, making of carbs from non-carb sources. Okay. The purpose of doing those 2 things when we release cortisol is to help us resist stress. And that's why it's known as a stress hormone. Cortisol plays a part in inhibiting the effects of white blood cells that participate in inflammatory responses, which explains why excess stress can impair the immune system. We're going to talk about that in a little bit. Low blood levels of cortisol will stimulate the release of corticotropin-releasing hormone from the hypothalamus, which then we know a releasing hormone from the hypothalamus stimulates an anterior pituitary hormone, ACTH, which is adrenocorticotropic hormone, adrenocortico, so there's where that half of the word comes from. And that hormone specifically stimulates cortisol release. The final set of hormones, called androgens, from the reticularis, have masculinizing effects. I'm not even going to try to pronounce that word, DHEA. It's really not discussed much as far as what it does in men. It does a little bit in the book, but I went ahead and just kept it out. But in females, it does promote the female libido or sex drive, and it's converted estrogens in other body tissues, which we'll talk about estrogens before the day is up. So those are the adrenal cortex hormones. Here is that mechanism that we'll talk about later in the semester. And now we get to talk about some of those other words, because the hormones from the pancreas produce those responses. And we're going to talk about the pancreas in greater detail when we get to the digestive system, because it is one of those organs that participates in both the endocrine and another system. Actually, 99% of the cells of the pancreas are dedicated to digestive purposes, which leaves only 1% of the cells that we collectively call pancreatic islets, or islets of Langerhans cells. And these are the cells that produce the 4 hormones that we're getting ready to talk about. Those 4 cells are alpha cells, beta cells, delta cells, and F cells. Let's first talk about alpha cells. They secrete the hormone glucagon. I always tell students, if you can remember the phrase, glucose is gone, it will help you. Because that sounds a lot like glucagon. That's how I was taught to learn it. We're talking about its stimulus for secretion, which is hypoglycemia, where hypo means low, glycemia means blood sugar or glucose. Blood sugar and blood glucose, the same thing. Okay, so there's the stimulus for secretion. One of, anyway. Another stimulus for secretion would be the sympathetic nervous system, which we know produces that fight or flight response. And what do we need in that fight or flight response? ATP, energy. Where do we get that ATP or energy? From glucose. So it stimulates or simulates a low glucose effect, so that we release glucose into the blood in a process called glycogenolysis. That's one of those terms over there on the board. Glycogenolysis has the word glycogen in it, and lysis telling you that it is the breakdown of glycogen into glucose. And we also will convert amino acids into glucose, which is that same term we saw on the previous page or 2 pages ago, gluconeogenesis. So there is a third function or stimulus for release, which is protein-heavy meals. And most of the time, though, we're going to probably have some form of carb in our diet as well. And so we will, instead of releasing glucagon after a meal, we'll release insulin. Release insulin from beta cells when we are hyperglycemic, high blood glucose. So these two hormones are antagonistic, just like the hormones we saw with calcium a little bit ago. Insulin promotes the movement of glucose into tissue cells when blood sugar is high. I said just a little bit ago, but glycogenolysis and glycogenesis are opposite processes. Glycogenesis is the process that we're talking about here. Making glycogen from glucose. So taking the glucose from our blood, making glycogen. We can also stimulate the production of lipids by way of insulin, which is called lipogenesis. Okay. And then delta cells secrete somatostatin, inhibiting secretion of insulin and glucagon, slowing absorption of nutrients from the GI tract. There's not really much to know about that guy. F cells secrete pancreatic polypeptide, which inhibits somatostatin, contraction of the gallbladder, secretion of the pancreatic digestive enzymes. Meals that contain protein, a fasting state, exercise, and acute hypoglycemia will stimulate its secretion. Okay. Here on this figure, we show something similar to what we showed with calcium homeostasis, except this is glucose or blood glucose, blood sugar homeostasis. We're showing the cells releasing either glucagon or insulin in response to either hypoglycemia for glucagon, hyperglycemia for insulin, and all those processes we just talked about help to maintain a normal blood glucose level. Before we move on from the pancreas, I want to talk about the most common endocrine disorder, which if you haven't looked ahead, sheet, anybody know what it is? Diabetes. Diabetes mellitus, which results from generally one of two things: an inability to produce insulin or a resistance to it, which means that you can't use it even though you produce it. Now there are several types. The two primary types are listed here that you have to know: type 1 and type 2. Type 1 is known as insulin-dependent diabetes because these people have to inject or have an insulin pump to get their insulin because their body doesn't produce it anymore, and it is because the immune system destroys the beta cells that produce the insulin. Okay. So insulin dependent versus insulin resistant, which is what type 2 diabetes is. Type 2 diabetes is where the individual ends up producing too much insulin and their body becomes resistant to it, and it has everything to do with the fact that their blood sugar levels are typically way too high. Which of those is more common? Anybody know? Type 2, and it's not even close how more common it is. Okay. It is hugely more common, or greatly, probably be a better word than hugely, greatly more common than type 1.
As far as like people who don't have it.
People that have it. There's a lot more people with type 2 than type 1. Much more common. Anybody know why people get type 2 diabetes? Lifestyle, mainly, is what causes it. Poor diet. Poor exercise levels. Unfortunately, it's very common here in the United States of America and other industrial countries. So we can sit on our phones and eat all sorts of crap that is available at McDonald's just down the street. And it's also therefore treatable by changing lifestyle. Okay?
They say they think they've had a cure for type 1 though.
Yeah, I've seen stuff on that. Now, type 1 used to be known as juvenile onset, and type 2 used to be adult onset. Why don't they like that terminology anymore?
Getting type 2 now.
Kids are getting heavy, not getting off the couch, not off the iPads, and now you see type 2 diabetes in kids, which sucks because it's completely preventable in that case. But kids are still getting it, along with other big-time health issues. All right, another set of glands, or organs, I should say, that we're going to talk about later in the semester because they are not just endocrine in function. These gonads, as we call them, are reproductive in function. Gonads are the ovaries in females, testes in men. These will be discussed in much greater detail later in the semester. They produce these hormones that are listed here. They also produce the gametes. Gametes are egg and sperm, sex cells. Okay. Females with their ovaries produce several types of estrogens. That's not a spelling error there, or typo. It's plural. Okay, unless most of the time you hear people say estrogen, but it's actually multiple hormone. They're involved in the maturation of the ovum. Ovum is the mature egg, which could be fertilized by sperm. And if the sperm is going to fertilize the egg will now, or what's formed zygote, will then insert into the uterus. And so estrogens also help get the uterus ready for fertilized egg. Estrogens are also involved with the development of secondary sex characteristics and closure of the growth or epiphyseal plate. Okay. Secondary sex characteristics of females would be, development of the breast tissue, growth of pubic hair, underarm hair, that kind of stuff. That takes place when females hit puberty. Progesterone is a hormone that promotes glycogen storage and growth of blood vessels in the endometrium. Endometrium is the inner lining of the uterus, by the way. It also helps grow the secretory cells of the mammary glands, getting those ready to start producing milk. Inhibin does exactly what it sounds like. It inhibits FSH. Remember, FSH, follicle-stimulating hormone, we talked about on Wednesday, is the hormone released by the anterior pituitary that targets the ovaries. It also targets the testes in men, and so men produce inhibin in their testes that does the same thing. Okay. Relaxin is another hormone that does exactly what it sounds like. It helps get the female body ready during pregnancy for childbirth. So it relaxes some things, as you can see, dilating the cervix, increasing flexibility, pubic symphysis, which helps the hips kind of open up a little bit more. The other hormone listed here I haven't talked about, which is produced in men, testosterone, stimulates the descent of the testes before birth, allowing them to travel down from the abdomen where they develop into the scrotum where they will remain. Regulates the production of sperm. That's its major function, what we call spermatogenesis. Maintains male secondary sex characteristics, so gives guys their deeper voice. All sorts of hair all over the place because men are real hairy. All sorts of other things as well. And then aids in the closure of the epiphyseal plate, that growth plate, just like it did in females. The next structure should be familiar to you guys. We've talked about it before. Pineal gland up in our brain, part of the epithalamus. We learned previously it produces melatonin, which we don't want to confuse with melanin, as we know. It gives us our skin color and our hair color. Melatonin, we know, sets our biological clock. What's the fancy way for describing our biological clock? Circadian rhythms, which, despite what a lot of you guys put on your test, is not your heart rate rhythm, but it is your sleep-wake cycle. And we produce more melatonin at night, and therefore we think that it causes you to feel sleepy. Okay. And that's demonstrated with the figure here. At daytime with light, it inhibits the secretion of melatonin, versus at night, it excites a tract that eventually innervates the pineal gland to release the melatonin. Here in Kansas, we don't have too much trouble with this because we have good, distribution of night and dark, night and day, as in dark and light. If you live up in Canada or Alaska, where you end up with like 20, 22 hours of daylight a day, you really have to take some extreme measures in your house, plugging up windows and that kind of stuff to make it dark to help get yourself to sleep. You can also take melatonin you can get it over the counter, so people use that a lot of times to treat kind of sleep, not sleep apnea, but lack of sleep, insomnia, that kind of stuff. My nephew's on it because my sister-in-law thinks my nephew won't ever go to sleep, which is very true. All right, another organ that we'll see later in the semester is our thymus. Produces a whole bunch of hormones. I don't care about you knowing every one of those names. Just know those as the thymic hormones. It's fine with me. And their function is pretty simple. They help our T cells mature. T cells, or T lymphocytes as they're fancily known, are some of the major soldiers of our immune system. So these are white blood cells that destroy microbes and foreign substances. And these are things that we'll talk about when we get to the immune system lecture. As mentioned earlier in this lecture, there are cells and organs other than those usually classified as endocrine glands that can secrete hormones, therefore having an endocrine function. The table there on the right, it says following table, it should be table on the right, provides an overview of these structures, the hormones they release, and their hormone action. Some of those we did talk about, like estrogen and progesterone. Those are discussed. We talked about calcitriol. Some of these we will talk about later in the semester, and I'll say, hey, remember when we talked about them previously? And I will do that. Okay. That includes gastrin, secretin, cholecystokinin, hormones that help regulate digestion. So when we get to the digestive system, we'll talk about those. When we talk about reproduction, we will talk about HCG, human chorionic gonadotropin, which is the hormone that a female will pee on a stick to test if she's pregnant, which my wife did a couple weeks ago, or about a month ago. And we found out we were having children, or another child, I should say. So that's exciting for us. We won't talk about the HCS. We did mention renin, and that we'll talk about it later in the semester. We'll talk about EPO, which helps us make our red blood cells. We'll talk about AMP, which helps regulate blood pressure, blood volume. But we don't really even get into leptin, which is actually produced by your fat. And so as far as the table goes, for right now, you don't need to worry about it. But I just wanted to present it because we're going to talk about it later in the semester. So you can refer back to it later if you want. So all these hormones that we've been talking about are all examples of circulating hormones, which we know circulating hormones are those that are released into the blood and then carried to their target organs. But I mentioned the other day that there were paracrine and autocrine hormones, which are the two types of local hormones. Okay. So we'll talk just briefly about a couple of local hormones. So two families of eicosanoid molecules are found in virtually all body cells except for red blood cells, where they act as local hormones. And so let's talk about prostaglandins, which do a whole bunch of different things. Okay, some of these things we'll talk about. Some of them we've actually talked a little bit about, like nerve impulse transmission we've talked about. We didn't talk about prostaglandins in their help or aiding in that. But we will talk about prostaglandins like when we get to the cardiovascular system. Okay, it alters smooth muscle contraction, which we have those in our blood vessels. So therefore affecting blood flow. Inflammation is something that we'll talk about with regard to blood flow and our cardiovascular system and lymphatic systems. Fever is a function of the immune system, and we've talked about pain before, so you can kind of read through that, see what prostaglandins do. Leukotrienes, we don't really talk about those too much in here, but they stimulate a process called chemotaxis, which we do talk about, which is where white blood cells target parts of the body that are in danger because some damage occurred or an invasion has occurred. Okay? It's part of an inflammatory response. I'm sure you've all heard of aspirin before, maybe even taken. Pain and inflammation reliever, blocks the synthesis of prostaglandins involved in pain mechanism, and prostaglandins involved in blood clotting. A lot of people take an aspirin a day because it's a blood thinner, quote unquote. Okay. Blood thinner is really a poor term. It doesn't mean that your blood becomes thinner as in more watery. A blood thinner just prevents blood clotting. And people take aspirin in order to prevent things like a heart attack, which can occur when your blood clots. Okay. Last set of hormones, I believe these are the last that are similar to the hormones that we talked about previously, growth hormone, thyroid hormone, insulin, in that they stimulate cell growth and division. We call these hormones growth factors. You can see those in the table over there, all have growth factor attached to their name, which is important because they help to device or grow, but also for tissue development, repair of damaged tissues. We call these mitogenic substances because they promote mitosis. What's mitosis? Cell division. Mitosis is a fancy word to describe cell division. As far as the table goes, you don't need to worry about those individually. Just know what these growth factors are and what they do. Promote mitosis, therefore being mitogenic substances. Very last thing I'm going to talk about is stress, which unfortunately, but not unfortunately at the same time, we all experience. Most of the time, we think of stress as a bad thing, and I can see Blair smiling at me back there, because she was probably thinking about the stress that she's under for this test on Monday. If you do not have stress, you would never get out of bed. You would never do anything with your life, because there is positive stress that helps us in our everyday life. That type of stress is good, and we call that eustress. Hopefully you get to demonstrate that this weekend as you study. And don't blow off the test, because that will be a bad consequence. Hopefully the stress doesn't lead to some bad things. Where stress is harmful to the body, we call it distress. Now, when I talk about stress, most of the time people think of it as like an emotional reaction. Okay. Well, a stressor, which is anything that produces a stress response, can be just thought of as anything that impairs homeostasis. And we've talked about things that impair homeostasis. Something as simple as being outside on a cold day. Or it could be as complicated as a toxin, or poison, or a hemorrhage. Regardless of what it is, our body is going to react using the stress response. also known as the general adaptation syndrome, which involves 3 steps or 3 stages. Sometimes we end up going through all 3. Sometimes maybe it's just 1 or 2. The immediate response to a stressor is activation of the sympathetic nervous system. And we know that's going to produce that fight or flight response. And so this involves our hypothalamus, which then triggers a lot of different things to adapt our body for physical activity. Increasing glucose and oxygen in the brain, skeletal muscles, and heart, while inhibiting digestive, urinary, and reproductive activities. Since we shut down blood flow to our kidneys will interpret that as a lack of blood in our body, which will trigger the release of renin, which renin is part of that renin-angiotensin-aldosterone mechanism, which will do everything in its power to conserve our blood and elevate blood pressure. So that's kind of tying in something that we've and will talk about later in the semester. The second stage is our resistance stage, where we resist the stressor. It is longer in duration than our fight or flight response. It involves those hormones from the hypothalamus that are classified as releasing hormones. Mainly talking here about corticotropin releasing hormone. But we also have thyrotropin releasing hormone and growth hormone releasing hormone that help to stimulate the release of hormones from the anterior pituitary, which then stimulate eventually the release of things like cortisol. But we also have T3 and T4 from the thyroid. And then directly from the anterior pituitary, we have growth hormone. Those kind of 3 major, T3 and T4, kind of we'll just combine to one. But also cortisol and growth hormone help to resist the stressor. And how do we resist stress? With energy. Energy in the form of ATP. Now, just like your car, eventually you can run out of energy or gas. Hopefully, you don't, because this is the stage where you can be at risk for getting sick. And that's the exhaustion phase. Occurs when the resources of the body become so depleted that they cannot continue the resistance stage. If you have prolonged release of cortisol, it will impair your immune system, waste away your muscles, lead to ulceration of the GI tract, and even cause your pancreatic beta cells to fail, therefore not releasing insulin. Not a good thing. Not a lot of good things, actually. Although the exact role of stress in human disease is not known, it is clear that stress can lead to particular diseases by temporarily inhibiting certain immune system responses. Stress-related disorders include gastritis, which would be stomach inflammation, ulcerative colitis, ulcers in the colon, irritable bowel syndrome, a lot of digestive issues. Hypertension. What's hypertension? High blood pressure. Asthma, rheumatoid arthritis, migraines, if you don't know what those are, anxiety, depression. All stress-related components. Some of you guys might suffer from some of those. Okay. I have no idea for sure. Here on the final page, we show just how complicated this stress response is. We have the immediate fight or flight response with all the different things that occur there, mediated by the sympathetic nervous system, which, as we know, activates the adrenal medulla to release epi and norepi, but also just the sympathetic nerves that actually directly innervate the various things in our body. And then after that, the resistance reaction, where we release cortisol, human growth hormone, which then causes IGS to be released, TSH, which results in T3 and T4, and all those do their thing, all aimed at increasing ATP production so that we can resist the stressor. Questions?